Professor Dave and Chegg here. We know how to write equilibrium constant expressions, and we know what the equilibrium constant represents. But what are some applications of this constant? Let's discuss some things that K can tell us about an equilibrium.
First, we must recall the difference between K, the equilibrium constant, and Q, the reaction quotient. Q takes the form of the equilibrium constant expression, but involves non-equilibrium concentrations. This is a value that tells us where a system is at any given time. Only once a system reaches equilibrium does Q equal K, so K qualifies as a constant. It describes something fundamental about a particular system and the ratio of the concentrations of the substances in that system, specifically at equilibrium. The magnitude of K will tell us the yield of a reaction once it reaches equilibrium. If K is very large, much greater than 1, it means this fraction is very large in the numerator, so products dominate the reaction mixture. If K is very small, much smaller than 1, it means this fraction is very large in the denominator, so reactants must dominate the reaction mixture. But Q is also very important because it will frequently be the case that the components of an equilibrium will be present but at non-equilibrium concentrations, and will thus necessarily shift in one direction or another until equilibrium is achieved, as the system will spontaneously move so as to equilibrate due to a discrepancy in the rates of the forward and reverse reactions. Once we know the K value for a reaction, we can predict which way the equilibrium will shift given a reaction quotient for some non-equilibrium concentrations, since the reaction quotient must eventually become equal to K. If Q is bigger than K, it is because there are more products present than there would be if the system was at equilibrium, as the numerator is larger. Therefore, the system will shift left until equilibrium is reached, meaning the reverse reaction is favored. If Q is smaller than K, it is because there are more reactants present than there would be if the system was at equilibrium, as the denominator is larger, making this fraction smaller. Therefore, the system will shift right, meaning the forward reaction is favored. This is how we can compare Q to K in order to predict the direction in which a system will shift in order to equilibrate. We should also note that a reaction can begin from reactants, products, or from a combination of both. No matter what the circumstance, the system will move so as to attain equilibrium.
With that, we should have a better understanding of how Q and K correlate for a particular equilibrium system, and how to use these to make predictions about that system. Professor Dave for Chegg. See you next time.